We began the meeting yesterday by saying that this program is involved with identifying and addressing seismic challenges. And we said it's no small issue to determine what are the challenges. And so let's say additional word about that. We've made some comments about direct and indirect inversion. There's a paper on this subject that's just been accepted for the journal Interpretation. There's a memory stick in the back that has an entire annual report, including that paper. But the point is the following. Nothing that this group develops or delivers is the answer to all the world's problems, okay? It's never going to be the last word, okay? So let me explain what that means. That's not some kind of sort of rush of humility, okay? That's a statement of reality. So let me explain what that means. So let's say you have an equation that you decide is relevant to exploration seismology. You just decide, just humor me, yes? Imagine that this equation is relevant to exploration seismology. What that means is, it doesn't mean you can publish more papers, it doesn't mean you can get a promotion, it doesn't mean you can get tenure, okay? It doesn't mean whatever. It means that if you solve this problem, you will increase your drill success rate, okay? That's the measure of advance in seismic processing, seismic research. That's the only measure that's real. Everything else is an illusion, okay, in my view. So let's say you have a direct solution to this problem. In other words, just for a minute, because I'm going to go back to that elastic thing yesterday with the direct inversion. So a direct solution to this is, of course, known for many years, minus b plus or minus the square root of b squared minus 4ac over 2a. There's no search. You give me a, b, c, you get two roots. Direct. So let's say you settle on this, solving this problem is relevant to exploration seismology. You use this as a solution, and it does not improve your drill success rate. Just imagine that, yes? Then you know that this is not the issue, because that's a direct solution. You know that the problem you're trying to solve is not the problem you need to solve. So a direct solution provides two benefits, two unique benefits. One is it lets you know that you're solving the problem of interest. But more important than that, it lets you know whether the problem of interest is the problem you need to be interested in, okay? And that comes from whether the solution affects the drill success rate. Yes, that's the only measure. Yes, does it reduce dry hole drilling, for example? So that's a very important benefit. If you have an indirect method, and indirect methods have a tremendous advantage over direct methods. If you want to convince someone to support a research program, and you just have 2 minutes to talk about it, I suggest you talk about indirect. You give me a trace, I'll get a model, yes, I'll generate a trace from the model, and I'll try to match them. You get it? Of course I get it. Okay, here's the money. Go do it, okay? It's accessible, the thought is accessible, yes? So how you match and update and so on is irrelevant once they get the idea of matching. And that's indirect, because there is no solution like this. In other words, I could say, let me find ax squared plus bx plus c squared and minimize it, or LP norm, you know. I could go on and on. So there are many indirect methods for solving problems. Common image gather flatness. In other words, there was a time in that evolution of migration when you had time migration, and then you went to depth migration, a much more capable method with a much more demanding interest in an accurate velocity. If you did not have an accurate enough velocity, time migration was superior to depth, so people couldn't find that velocity directly. So they looked for indirect methods. Can I find a method which when I have the velocity would satisfy a certain condition, yes? And certainly common image gather flatness is a condition that a correct velocity model will satisfy. It's a necessary but not sufficient condition. At ARCO, we would have common image gathers as flat as a pancake, and the target was somewhere else because there were other velocities. We just happened to find one that we used that satisfied it. It wasn't the actual. There's a whole suite of velocities, including the correct one that will satisfy that condition, yes? So FWI is a model matching. It's not evil, it's not dangerous, it's a method, yes? What did we say yesterday in terms of how we view the role of direct and indirect? Direct for us is you write some Green's theorem, you write some inverse scattering series. As we said yesterday, those are concepts, those are models for the world. That's not the world, yes? The world is more complicated than anything we will ever write down, or I believe anyone in seismic research. It's beyond. Yes, it's extremely complicated, the subsurface. Look at Neil's, poroelastic and so on. Yes, the different levels of model. So the point is, we feel that take your physics, the part of the world that you've covered by the physics, and try to do that directly. And the part that's outside, there's no choice. You have no equation. You understand? It's by definition outside your ability to describe. It's there, but you're not describing it. For that, indirect. What other choice? Find some criteria, yes? So you saw. So the point is, yesterday, when you saw the direct inverse for the elastic wave equation, first of all, the people who contributed to that are Haiyan Zhang, Hong Liang, who was here from Aramco yesterday, Xu Li, Shenzong Zhang. Those are the pioneers who developed it. But let's say you have that direct method. It says you need a data matrix, and you need to do something to that data matrix. Let's say you settle on the elastic isotropic, and you start to find changes in lambda mu rho using that elastic isotropic. And then you apply it to your amplitude analysis. And it does not improve things. Just because you use a direct method doesn't mean it's going to improve anything. Depends on what you're inverting, yes? So if it doesn't improve, you know it shouldn't be the elastic isotropic because you have a direct solution. You follow? So we're not saying any of these direct methods are the answer. It gives you a way of not only, first, this tells you solve that. But more importantly, it tells you, should you be solving that, yes? In other words, if this doesn't improve your drill success rate, then you're solving the wrong problem. And problem identification is the critical part of research. What problem should you solve? That's why when you have FWI workshops, you have every kind of method in the world because it's indirect. Here's my matching, here's my matching, you understand? And if it doesn't work, you don't know whether you're not, the problem you're trying to match is the issue, or the matching method is the issue, or both. So you keep going. You understand? That's very important that we communicate that we don't think direct methods are the answer to the problem. Yes? They're a way of answering a model of something. And it also gives you an indication of whether you're solving the problem you ought to when you use it. Does it improve things? Okay, so that said, we're going to move. Yesterday what we covered was, we started off with a tutorial which had a math physics that covers everything in this program. And it's sort of two expressions. One is an expression for the wave field everywhere in the universe, that if you want the wave field everywhere in the universe, you have to have a math description of what generated that wave and everything that influenced that wave. And that became an equation where we assumed, let's say, some homogeneous background, and everything that created and influenced it was sources of either the active or the passive, looking for an instant wave, but sources. And then if you integrated G0 plus rho over the entire universe, you got the field everywhere. You give me what created, you give me what influenced, you get the field everywhere. That's a cornerstone of math physics, okay? And a separate form, which was only valid to give you the field inside a volume, was described, came from a very different origin. Its origin comes from Newton, Gauss, Green, which says you have an integral over something, an integral outside the volume, thinking how Newton would talk. Newton would say, I can replace this integral over sources outside the volume, what it contributes, by a surface. Integral of an antiderivative, of a derivative of something, is the function evaluated at the endpoints. I can replace an integral by just something at the endpoints. That's what Greenstem gives you, a way of taking into account the influence of sources outside the volume on the field inside through a surface integral, yes? And that form, which gives you the field in the volume in terms of an integral of the sources in the volume plus a surface integral on that surface of the volume, then forms the basis of several projects here. One is wave separation, deghosting, separating the reference field from the scattered or reflection data, yes? Another application is what you're going to see today, is migration derives from that same idea of predicting a wave inside a volume. What is the field inside the volume if I have surface measurements of that wave, yes? So these are the people who, this is sort of getting us ready for the progress this year. So the topic here is, this is the first migration method that's equally effective at all frequencies at the target and the reservoir. I'll repeat that, equally effective at all frequencies at the target and at the reservoir. So if you say it's the first, you better explain why everything today isn't, yes? So that's the first thing, yes? What is it about what we're doing today that is not equally effective, yes? So let's start the talk. Are there any questions about that? Okay. So again, if you want to see a paper that goes into all the direct inverse, not only direct inverse, in this paper we do a comparison for the simplest problem in the world. Let's say you have a normal incidence wave over a single interface, yes, just down, and you do direct inversion on it. How do you get the velocity directly compared to iterative linear? Forget about bandwidth, forget about noise, give the iterative linear full bandwidth. Those are issues, of course, yes? We're saying just look at the algorithms, and there's an analytic example there that shows the benefit in terms of convergence rate, okay? The region of convergence. The advantage of the direct is it always converges in that problem, yes? The iterative doesn't. It has a region that it converges, and when it does converge, it converges less rapidly in that simple case of straight up and down. So it's not a question of what data, it's just a P data, yes? One reflection. Okay. So we start with, we understand, and Professor Mark Meyer gave an excellent presentation yesterday explaining the industry-wide interest in increased low frequency. There's also, we hear from companies that there's an interest in not only acquiring low frequency data, but assuring we get benefit from it, meaning we get benefit at the target, at the reservoir from that. We hear from companies that they see the benefit. They look at the data in a given region with conventional acquisition, and then they look at the data with broadband, and they see a difference. They see the spectrum is different, naturally, and the shape, the temporal shape of the data looks different. They look at the migration with the conventional, yes, and what they're used to is RTM. When they look at the migration, with the conventional data and the broadband data that they pay a whole lot more money for, they don't see the type of advantage and benefit they anticipated from just looking at the data, yes? So we figured perhaps there's something about migration methods that is discounting the added information at low frequency, yes? Why is that happening, yes? So that motivated this. So the methods that take data from the surface and try to provide an image or do migration inversion are called migration and migration inversion. Naturally enough, we look at what are migration methods doing to the conventional versus broadband data. So two things are going to happen here. One is we're going to explain to you why, or demonstrate in this talk, that all current migration methods, one way or another, or more than one way, make high-frequency approximations. High-frequency approximations means it's assuming it's better suited, that approximation, the higher the frequency, okay? So if you get more low frequency in your data, it's not going to be well treated because it's aimed, it's designed to treat the higher frequencies more accurately. So one objective here is to convince you that all of our current migration methods, one way or another, make high-frequency approximations. The second is to provide a migration method that will not make any high-frequency approximation, and will be equally effective at all frequencies at the target and the reservoir, yes? We have to convince you that that new method is that too. We have to convince you that the current methods are high frequency, and the method that we're proposing and describing and illustrating and comparing isn't. What is it about that isn't? Okay, and then last but not least, once we convince you that this new method that we call Stolt CIII for heterogeneous media is not a high-frequency approximation, and that current methods like RTM are a high-frequency approximation, that's what this talk will be about. Then the next talks are going to be to quantify. If one is a high frequency and one isn't, can you quantify the difference in migration, yes? That in terms of resolution, for example, where, as we know, there are side lobes, and the more, and you just look at data, let's say for some Ricker wavelet, and you have side lobes, and if you the more low frequency you give me, there's a reduction in the side lobes, and they move closer, yes? The more low frequency. So we looked at the side lobe issue. In other words, when you have conventional versus broadband, what happened to the side lobe, yes? Did it reduce? How much, what fraction, what percentage did it reduce? And then after you look at that for one reflector, we'll examine it for a wedge, yes? When can you resolve two? That there are two versus, yes? And where do you start to think it's one for two different migration methods, yes? Because that's an extremely significant issue. If you don't think there's a layer, why would you start to look for permeability and porosity, yes? If you think it's a reflector, yes? So that's where we're going. And last but not least, there is a method here, a prescription, a formula, a recipe, if you like. How can we arrange, when you want to apply this new migration method to a heterogeneous media, how can you know that you are applying it in a way that will be equally effective at all frequency? Yes, a practical method, very clear and very much based on the physical interpretation of CIII imaging. Okay, so let's. This is just saying seismic acquisition, seismic processing should be consistent and aligned. In other words, if you're going to acquire lower frequency data that we encourage, we ought to look at our processing methods to assure that we're taking full advantage. That's all. Yes? So migration methods that use wave theory have two ingredients. One is an imaging principle, and one is some kind of propagation model. And we'll examine each of those in this paper, and then we're going to focus on frequency fidelity. There's a side benefit. There was a paper published in 2016, Multiple Signal and Noise, and we're not going to go through all the detail of that. But this new migration method for heterogeneous media gives you a definitive answer of the role of primaries and multiples in seismic migration. Okay? And then we'll say something about use of multiples. Multiples can be used. Okay? We have Dan Whitmore here, a key advocate for that, and we'll say what we view as the benefit of that approach. Where does the multiple removal and the multiple removal, where does the multiple removal and the multiple usage? If you say, oh, we're going to remove the multiples, and then someone says, I thought you're going to use it, okay? Can you make up your mind? You're going to remove it or you're going to use it? We're going to give our perspective on that issue, yes? Where they are not adversarial views, okay? The removal and the usage are not adversarial, okay? They all fit into one picture, yes? And that's what we'll aim to explain. Is that understood? Okay. So migration was originally and remains today only meaningful for primaries. The concept, you had a trace and you wanted to know where on a structure that trace originated, yes? One reflection and one position in space. That's what this is. So the most sophisticated method for migration, which we call Stolt-Claerbout 3, agrees with that, yes? It says, and you'll see that for the most capable method in terms of structure determination for specular, non-specular structural determination, amplitude analysis at both specular and non-specular structure, the method that's able to, for heterogeneous media, produce those kinds of images, yes, has a very clear message about the role of primaries and multiples in, for that kind of objective, yes? So we say we have two, so we're going to isolate. What do we mean by that? We're going to compare imaging conditions where the propagation models are analytic. In other words, there's no numerics to them. Okay, so there's whatever the issues are strictly imaging conditions. So if okay, so there's a landmark paper by John Claerbout, 1971. We just pick on this as a useful, very useful, important reference. Where in that paper, Professor Claerbout lists three imaging conditions: the exploding reflector model, which is for zero offset data, and the time and space coincidence of up and down going waves. In other words, you take your reflection data and you move it back. This was all for one-way waves, so you move it back in space. In other words, where does this up data come from, yes? And you take the source field, just let that field go forward, yes? And you look for where that down field from the source stays here. The field from the source is looked at, yes? And the data that's recorded is taken back in space originally, yes? Until they are at the same location at the same time, and that location where they're coincident, the same space and time, is where a reflector resides, okay? That was the idea, yes? The third imaging principle in Claerbout's paper says, imagine from surface sources and receivers that you can predict what an experiment of a source and receiver in the subsurface would produce. That there was a source in the earth and a receiver in the earth that you could predict. So you have some sources and receivers. Here's a source and here's its receivers. Let's say you can predict what a source and receiver experiment could be at depth. Then the idea in John Claerbout's third imaging condition is make this source and receiver experiment from first any two positions in the Earth, place them at the same position, okay? Place them at the same location, and then ask for t equals 0, small positive time. What that does is, in other words, if you just have the experiment here for all time, it cares about all the properties in the world. Yes? Yes? If you give it all time. If you ask for small positive time, it can only care about local properties. So if you have a reflector here, and you have this coincident source receiver over here, and you ask for t equals 0, you get 0, because it's only here it's going to be non-zero for a non-zero time. Yes? So if you say, what is the amplitude of this experiment when there's a source and receiver coincident, at the 0 time, the answer is 0. So you get no image here, you get an image here. It's that definitive, either yes or no. Yes? Once you have that experiment there, structure or no structure. Yes? Very defined and very interpretable. One very important point you'll see evolving this morning is this. If you have this as C0, and this is C1, and you have some wildest C of x, y, z here, this experiment here couldn't care less about what's above it. If you can predict this source and receiver here accurately, all it cares about these properties. You'll see how that's exploited. That's a unique benefit of Claerbout 3, the fact that it has that physical interpretation. Yes? Okay. Does anyone have a question about what I just asked? Okay. Or I just said? I think I need more coffee. I hope this coffee has got caffeine. Okay. So these three imaging principles, the first let me make it clear. If you have a plane wave straight down and back, yes, down and back, and you have that data and you want to locate this reflector from that reflection data, those three imaging principles are identical. Yes, they give you exactly the same analytic answer. They're no different. The 2 and 3, which are for pre-stacked data, will differ as soon as you have a source and receiver separated and you have a horizontal reflector. Okay? They will differ. That's what we're going to look at. So this is an example of Claerbout 3. This is an example, a Stolt migration, 1978, is a Fourier way of arranging for the experiment, yes, through Fourier methods. What that formula here says, this is the experiment at depth, and you've already put a t equals 0 here, and then what this is saying is you make a 0 offset there, and that's the d of xh, the offset variable is 0, is arranged in the Fourier by integrating over kh, yes, a simple sum. What that's doing physically, in fact, is taking an angle average reflection coefficient, you'll see, okay? So, okay. So Stolt extended Claerbout 3 in two very important ways. Two ways that are only able to be achieved with Claerbout 3. And we call those Stolt Claerbout 3 because he extended the original. So you'll see something here, Stolt C3. Stolt C3 means there was that original imaging principle, xh equals 0 at t equals 0. Yes, that's C3. Stolt's extensions are what we're interested in. The two extensions were he wanted to do amplitude analysis after he located, yes? So he wanted to keep the KH information. Okay, the KH, don't sum over KH, he said, yes? Use that information. That gives you angle dependence at the structure. And so that led to a method called migration inversion. Clayton Stolt, Weglein, 85, a bunch of papers based on that loosening of, in other words, what it's doing is it's in fact letting XH not be zero. So that when we wrote that paper, it, how can, if you have t equals 0, how can you have XH not 0, yes? So it's, first it's a singular function there. It's a singular function at XH in the vicinity of XH equals 0. Also depends on the order of those limits. But that singular function, it's a very sharp function in XH. It's a function, in fact, which is even, it's like a delta of XH, delta double prime of XH, delta fourth of XH. It has to be even in XH for reciprocity, yes? And you have coefficients, A delta of XH, B delta double prime of XH, C delta fourth derivative of XH. And that leads to AVO. In other words, the conjecture was you have something like A delta of XH. In other words, what do we think at XH being small, as t goes to 0, the form will look like, yes? Some delta-like thing, perhaps, and then B delta double prime of XH plus C delta, in other words, has to be even. You don't want delta prime because it's an odd function. Odd function won't satisfy reciprocity. You understand? So we needed reciprocity. So then if you Fourier, these are very sharp functions. Sharp, you'll never use it in that domain. You go to KH, this in the Fourier transform of this is 1. The Fourier transform of this is KH squared. This KH to the fourth. You're getting A plus B sine squared, C sine to the cosine to the, you're getting your AVO from the KH dependence. So it's very sharp in XH at t equals 0, flat in KH. That's the place you go. You understand? So that led to one extension. That's definitely due to Stolt, okay? There were co-authors, but it was his thought, yes, to relieve that, and that was considered controversial, of course, like every other thought. So there's a second extension that Stolt, al. It's Stolt. He generalized this using linear inverse scattering to make the model to be, in other words, and when you do this first, this thing looks like AVO. In other words, some kind of specular, you know? You follow? Looks like he introduced point reflectivity, which is in published earlier, but also in the book that Stolt and I published in 2012, Cambridge University Press, Chapter 8, okay? Where automatically the extension that Stolt provided to Claerbout 3 automatically images and allows you to invert specular or non-specular, okay? Non-specular, including pinch-out, yes? So that's a major advantage, and it's our view and Stolt's determined view that that extension is only achievable with Claerbout 3. And most of the book, that volume 1 of the book, is Claerbout 2. It's RTM kind of, he's gotten all into that. So it's not like he's on some kind of anti-RTM business, yes? If you look at the book, it's plenty of RTM. He just makes a statement that the Claerbout 3 is able to be extended in a way, and people have extended. We have Dan Whitmore, the original Claerbout 2 was in depth. Take the data back in depth. Take the source field forward in depth. A major contribution which led to RTM was take it back in time, yes? That allows this, not just back in depth. Two-way, okay? So that was a major progress for Claerbout 2 and other extensions. I'm sort of running ahead of some slides with Bleistein, Sheng Zhu, yes, Yu Chang, yes. They were looking for an amplitude analysis to come from Claerbout 2, yes. And their amplitude analysis gives you a geometric optics reflection coefficient. They assume that the wave that's coming up, that's being brought back, is a geometric optics reflection coefficient times what went down, yes? So they can output a geometric optics reflection coefficient. You cannot get a non-geometric optics reflection coefficient from Claerbout 2. That's an important point, okay, that we'll use as part of an argument. Okay, so let's take a look at Stolt and collaborators, okay. We already said this. This is a typical Claerbout 2 RTM form where you have reflection data that's taken back and the source field is taken forward, yes? And you look at a time-space coincidence. You do that for one shot record, and then you sum over shots. We'll discuss that process. On the bottom is a comparison of a Stolt form of Claerbout 3, yes? When you, for one shot record in Claerbout 3, for one shot record, you can predict what one receiver would do in that volume for that source, yes? So it doesn't provide an image. One shot record does not provide an image in Claerbout 3. After you get the receiver predicted inside the volume, you do reciprocity, yes? And you, again, bring the receivers down, actually sources, yes? So you have to do a sum over sources to bring the source down, yes? So it's the sum over receivers that brings the receiver down, then a sum over sources brings the source down to have the source and receiver both at depth, okay? Very, that's what's going on here, okay, in the Fourier domain. You'll see a Green's theorem equivalent soon. Okay, so let's examine Claerbout 2 and 3, where the imaging condition is the issue. What we mean by that is how anything was implemented in these tests, whether it's arranged for that experiment or take the data back or take the source field forward. Those activities were done analytically here. There were no numerical. Why? Because we're going to be looking at strictly the difference in the imaging condition. If you look at how it's implemented, you're mixing. We'll look at the implementation issue after, okay? So this is Yang-Li Zhou. This is looking at a Claerbout 2, a single, this is what a single image looks like from one source, taking the data back and the source field forward and looking at space-time. This is well recognized. The image on the bottom is a blow-up. There's an inconsistency, okay, in the image. So what people do is they sum over sources as if there was noise, yes? They sum over sources. And then they get a consistent picture, whatever that means, okay? Summing over sources. What's the physics to that, yes? This is a Claerbout 3 result. With Claerbout 3, to be fair, you can tell the algorithm it's a 1D method, okay? You can tell it's 1D. If it's 1D, it doesn't care about midpoint, yes? And so this is really for one shot record, but it's been told it's a 1D algorithm. For RTM C2, you can't tell it that is the problem, okay? If you could, we could, but I just want to be clear. But for one shot record, this is a consistent picture that you get from C3. You don't have to fix it. Okay, we already said this. There's a fix for the Claerbout 2, where there's a sum over sources. In Claerbout 3, if it wasn't 1D, If it wasn't 1D, you have to do some sum over receivers for one shot to predict the receiver. That does not, you don't claim that's an image. You're not going to sum over sources to fix that. There's no image there. You just brought a receiver down, yes? You have to sum over sources to bring the source down, not to fix the problem with one shot record. You understand how different that is, yes? Okay. So how do you know if a migration method has made a high frequency approximation? Because I made a claim that all current migration methods are high frequency approximation, yes? There are indicators. Some are clear and some are subtle, yes? So if you have a picture like this in your migration, where you have a source and receiver, and you have a single reflector, one source, one receiver, you have one event, and that event goes on a travel time curve, yes? In the migration, yes? That's ray theory. That's high frequency approximation. This picture says, ray theory says, these are potential reflectors, yes? That's a ray theory picture. You give me a time, and the time for this are all the same, yes? That's not wave theory, okay? As soon as you do that, so if you see a picture like this in some intermediate step within your migration where it's looking for candidates, this is a candidate set, right? You give me a time, you put it on where it might be, and then you do it for other, yes? And then you look for constructive interference of possibilities, yes? You understand? That's ray theory, high frequency approximation. So here we have on the right, you have a comparison of a C2 on the right for one source, one receiver, one event. What happens in an RTM form with C2 versus what happens with C3, yes? So this form here is a set of candidates, yes?
So is the C3 there, is it assuming it's a 1D median? Does it factor the midpoint out of the interval?
I don't believe so. No. But that's a good question. I don't believe so. I think each just, in other words, the picture on the right, because of the C2, says.
It's just a question. We can come back to offline.
No, but I think it's an important question. You have a source and a receiver in C2, in RTM. In principle, one shot record should give you an image. That's the thought. Then it doesn't quite work, so let's sum over sources, yes? In principle, that's C3 for one source and one receiver is not anything near. We need lots of receivers just to get the receiver down, yes? So this is some kind of partial result, hard to interpret, yes? It's, but it's definitely not a travel time picture. That's the point. So what are so one indication of whether, for example, let's race ahead. If you take, and we'll go back to that last slide in a minute. Let's say you take a C3 form Stolt migration and you do stationary phase here with these integrals, high frequency approximation. You derive Kirchhoff migration, yes? Kirchhoff migration, which, look at the formula here. It says take that time and put it on R over C, yes? And you get that picture, yes? And that's what you get for RTM. You understand? The same kind of picture for one source, one receiver, and ask what is its contribution, yes? In other words, isolate it. RTM doesn't say to take one source and one receiver, yes? But within that procedure, which wants an entire shot record, you can ask what does one receiver contribute? And you get this. The others will give you these other candidates, yes? So it's very Kirchhoff-like is the point, in the sense that it's seeking coherent combinations of candidates. Please understand the difference between that and C3. Claerbout 3 says, you put a source and receiver in the earth, yes? Make them near each other at time equals 0, and you get a yes or no for structure. It's not a candidate. It is, you do that procedure, it isn't a possibility. If that's a non-zero value, there's structure. If there is a zero value, that point, no structure. You understand? There's no combination of candidates in C3. Understood? Very different in its origin. It's not seeking coherent sums. But going back, this is an important, very important point for our discussion. So if you see some stationary phase approximation, you know you've made a high frequency approximation. If you see a travel time of candidates, those travel times are based on a ray theory picture. Yes, that's that. And but there's a subtler point, and it's the major point of this talk. If you have a homogeneous medium, in other words, there's another way that high frequency approximations move into migration. And this is the major point, because Stolt-Claerbout 3 is not new. What did we do that's new? Yes? That imaging, with all its ability to do specular and non-specular, is well in the literature. Yes? What we did is arrange for that experiment in a heterogeneous medium. Okay? So let's explain. And to arrange for that, well, don't you have Stolt-Claerbout through in heterogeneous media already? Yes, of course we do. WKBJ, look at Stolt-Weglein 85. WKBJ is assuming in a smooth medium at every point the wave is moving in one direction, down. Okay? If you have a homogeneous medium and you have a wave in a homogeneous medium, it travels at that point in one direction, only for a homogeneous medium. If the medium is in any way not homogeneous, smooth, and you assume that at this point it's traveling in one direction, you've made a high frequency approximation. Okay? Let me repeat that. If you have a heterogeneous medium, anything that deviates from homogeneous, and if you assume in your wave propagation component, yes, there's a propagation component and there's an imaging condition. We're talking about the propagation component. If you assume, for example, if you're doing RTM and you do this, it's two-way in a macro sense, but it's one-way in a micro sense. At every point you're zooming down, 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 up, up, up to the reflector, yes? If you're doing that, this propagation model is high frequency, okay? So what we're about is to, for any heterogeneous media, assure that you have not made a one-way approximation, yes, in your propagation model, yes? And how do you arrange that? How do you arrange it, and how do you arrange it practically? Or what should you do? If Scott Morton or Uwe have a velocity model, what should they do in practice to arrange for that kind of thing to happen? Or Corey, yes? You have a velocity model. We're going to say exactly what to do, okay? So that's the end product of this several talks this morning. So, okay. So, Yu Zhang, Sheng Zhu, Norm Blystein extended Claerbout 2. As I said, Dan Whitmore made the mid-'80s other people, but he was the lead in extending Claerbout 2 in time rather than depth. A major contribution, yes? That was a heresy at Stanford. It was one way. And we understood that Clayton was an intern of yours, saw what you did, went back to SEP and couldn't talk because of proprietary. Because there, everything was one way. Everything evolves, but that was a major contribution, and Amico in the mid-'80s, yes? There were others, McMecken, but you were the lead on that. And these people extended it in terms of, as I said, those three, producing a geometric optics reflection coefficient. The extensions that Stolt of Claerbout 3 produces a plane wave reflection coefficient when there is a plane specular reflection. If there isn't, what if you have a curved boundary like that or a pinch out and you want to not only do structure but amplitude analysis? Stolt's extension is to point reflectivity. You get the amplitude of what would happen if a plane wave was incident on that curved boundary. It diffracts, okay? It doesn't, yes? And that is automatically done. You don't have to know, okay? There's a form of imaging model that looks at the data at the image. How does it know? For one particular plane wave, it looks at the spread. In other words, if there's a normal, yes? In other words, it doesn't need to know what the normal is, but it'll know for a given plane wave, is the data that's leaving when you do the imaging localized about some direction. If it is, it's specular. If it isn't, that you have that more general form that accommodates it, yes? Automatically by whatever the data is at the image. Please see our book, Chapter 8, okay? If you need a copy, I'm happy to give you. Volume 1, Chapter 8, talks about that specular, not specular imaging, the extension that Stolt provided to Claerbout 3, yes? Okay, how that works is in that chapter. That's more than we can do here, yes? Okay. This shows the difference between, this is Yang-Li Zhou, the difference between a plane wave reflection coefficient and a geometric optics reflection coefficient. If you're doing AVO or any kind of amplitude analysis, and you go to Aki and Richards and look at Zopritz or Bortfeld, they're talking about plane wave reflection coefficients. They're not talking about geometric optics. Well, if you're doing linear, maybe that's not such a bad thing, but if you're talking about nonlinear amplitude analysis and your reflection coefficient that you've outputted is damaged to begin with, you're taking that reflection coefficient very seriously, you know, in a nonlinear. So I suggest you take a look at what Stolt suggests for outputting a reflection coefficient. That's actually what a plane wave will do, not a geometric optics approximate, yes? Okay, so this says, okay, so all RTM methods are based on that Claerbout 2 imaging principle, and they all have that travel time picture, and they all are high frequency, no matter how you implement them. The imaging principle is already that, yes? Under perfect wave propagation. The Claerbout 3, the Stolt Claerbout 3 or Claerbout 3 by itself, the imaging principle is not high frequency. It doesn't have a travel time curve, and in addition, please listen to this. The extension that Stolt was able to do to Claerbout 3 to give specular and non-specular amplitude is an indication that it was able to be extended in a non-high frequency approximate way. It wasn't forced to be geometric optics, yes? Those are two indicators that the Claerbout 3 imaging condition is not a high frequency approximation. Now you can implement Stolt Claerbout 3 in a way that makes a high frequency approximation. Yes, heterogeneous and make a one way. We're going to describe how to apply that, how to arrange the propagation model so that you you do not make a high frequency approximation. Why is this? You're looking at resolution differences, yes? So we want to make both the imaging condition and the propagation model not making high frequency approximations, to be equally effective at all frequency. Now, I'm going to tell you something now that I'm sure people will just take away as the sum total. We are not, Jim O'Connell was here from Shell last year, asked the great question. He said, what about absorption, you know, in the overburden? We are not saying that you're going to have an effective migration at every frequency. We're saying, given whatever you determine the velocity is, which we're not providing, yes? With absorption, without absorption, we're going to be imaging through what you have determined is the velocity, yes? in a way that's equally effective. If that velocity is not correct, that will affect, yes? That's a different issue, yes? So there's an assumption here. When we say, as I joked last year, I said, you might say this method is equally ineffective at every frequency. Whatever it is, it's not prejudiced by frequency is the point, yes? In other words, if you give me a very wrong velocity, that image is not going to be correct. You didn't produce that experiment, yes? But whatever that experiment is, it's not going to be prejudiced. It's not going to be favoring high frequency versus low. That's all. That's what we mean by equally effective at every frequency, not effective at any frequency. It takes more than what we're doing. Is that clear? Okay. So what we've done is arrange for two-way waves, meaning for heterogeneous, to avoid high frequency. And it'll give a definitive answer of the role of multiples in migration. So we start with this. If we're interested in Claerbout 3, we're interested in predicting what a source and receiver will be at depth. So we start with this equation that we, something a little funny on the bottom here, but this equation, as we said yesterday, assumes that you know the properties in the volume, yes? There's a volume integral with G0 plus k squared alpha p. Alpha is the difference between actual velocity and the velocity you've chosen. We're assuming that the chosen velocity is the actual in the volume. Yes, so there's no volume integral. So you have this surface integral. This says if you give me a boundary information about P, I can get P inside, as long as I know the medium. And okay, so it's assuming that your P satisfies these P and G0 satisfy these equations where C of R is the velocity configuration in the volume. So you have this surface integral. The issue, of course, is we only have measurements on top. Yes? We only have measurements on top. And so even though the Green's theorem wants around, we have to arrange to be able to predict this field in the volume in terms of measurements on the upper surface. Green's theorem does not give you say that from this surface you can predict in. It says a closed surface. Okay, so there's a lot of people go off track with interferometry, forgetting about that other surface. Yes. Andrew Curtis, we've talked about that for some of his work. Yes. There's no guarantee that it starts with a closed surface. Yes, you got to worry about the bottom. Okay. So if you have a wave that you're trying to predict in the volume, which is moving up in the volume, always moving up in this volume, for example, homogeneous medium is moving up, or you're assuming it's heterogeneous and it's moving up, which we won't, okay? But if you did, as long as you assume it's moving up, then if you choose in that form, the strength of this equation is that any G0 of del squared plus omega squared over c squared of r, G0 equals delta, any solution to that G0, we emphasized that point yesterday. It doesn't have to be causal or anti-causal. Any of the infinite number of solutions for G0 will predict P in the volume, as long as G0 satisfies the properties in the volume. In other words, as long as G0 is that. So if you have a wave that moves up, you can prove that if you choose an anti-causal Green's function, then the contribution from the bottom will be 0, and it'll only require data on top. You can show that. Basically what it's saying, if the wave is moving up, the anti-causal tells you what it was from what it is. Yes? You understand? If I chose, for a wave moving up, if I chose G0 plus, this would only contribute and not that. because this would then tell you the future, yes? The wave that moves up in there would be from here, what will happen. The anticausal tells you what was it from what it is. You measure it, what was it, yes? So that anticausal will do that for one-way wave. And you, in addition, you could arrange for the Green's function to vanish on the upper boundary so that you only need the field, yes? You only need the field. In other words, to do wave prediction, this is very important. To do wave prediction, you don't need the field and the normal derivative. This formula, if you give me the field and the normal derivative, this works fine for any G0. But you give me the field only, or the normal derivative, or some linear combination, that will predict the field inside. It's called Neumann, Dirichlet, right? Like that. Yes? If you want to do wave separation, like deghosting, has to be the field and the derivative. You're separating the wave. It's up-down separation, if you want to think in simple terms. A, e to the I, k, z, b, you need two quantities, yes? To do wave separation like deghosting, you need field and derivative, or field and wavelet, yes? Some two quantities, yes? As James was asking about that, yes? So this you can arrange the Green's function to vanish on the surface, and that'll give you a p only, or you can arrange for the normal derivative of the Green's function to vanish on the surface, and you'll only need, so that's one of the, when you say any Green's function, that includes putting a boundary condition on it, yes? Why any? This is not superposition. This is a boundary value problem. You're giving me values of the field, and that nails it down. If these are causal quantities, that's a causal wave in the volume, no matter how crazy this is. This, for ordinary migration, that's a G0 minus, anticausal. That's not predicting a P in the volume, which is anticausal. It's just telling you a causal wave, what was it before? A causal wave, what was it before? Anticausal means it came into existence before the source. You understand? The Green's function and the P, this is always physical, no matter what this G0 is. Okay. So for if you pick this anticausal Green's function and you arrange it to have Dirichlet boundary conditions, in other words, that first term up here in a 1D world is an anticausal Green's function. You've added it to a term within image across the boundary, making that vanish on the upper surface, not needing the normal derivative there, okay? And you know what that leads to? That leads to this. P of A, you do a shift, you get P of Z in 1D, simple, yes? A wave moves up, you have it at P of A, you want it at P of Z, you do this. This is what all that Green's theorem boils down to. This is the normal derivative of an anticausal Green's function, yes? Anticausal Green's function that's been made to vanish at the upper surface. So Stolt shift here is a realization of that, yes? Again, this is not an anticausal wave, okay? This is just what it was before from what it is now. What it was before is still causal. You understand? You didn't predict an anticausal wave. You just took it back. What was a causal thing earlier? Okay, so now we get to the interesting part. We want to deal with, we don't want to assume for any kind of heterogeneity that the wave is moving in one direction at one point. So you can't depend on that G0 anticausal. What you have to do is you have to arrange for the contribution on the lower surface to vanish. So you have to arrange for a Green's function, what you call a G0 dn, we want a Green's function that vanishes and its normal derivative vanishes on the lower surface. So you give me the velocity model, we arrange a Green's function that vanishes along with its normal derivative on the bottom. What does that mean physically? God only knows, okay? It doesn't have any physical meaning. G0 is a useful side problem, chosen, okay? The only thing we're committed to physically is P. G0 is just one among infinite number of choices of its equation that's useful, yes? So that's not a simple thought, and it takes us a while in our math physics to explain that, yes? Why would we have a function that vanishes along with its derivative vanishing? Why? Because that's a convenient choice of G0 for this two-way problem. We don't want a contribution on the bottom, that's all, yes? So with that Green's function, you have you do a Green's theorem of a prediction of a receiver, and the source is up there. Then you do the same on sources, bring the source down. You have a double application of Green's theorem. And so this is one way. This leads to Stolt migration. This is what we advocate for two-way, meaning any heterogeneous do this. You will not be assuming here one way, okay? You just got rid of the bottom, yes? The question is, how are you going to implement it, yes, to assure? That's what we'll be discussing this morning. So this is an example. There's work, we all know, when you try to do Claerbout-2 RTM through a boundary, like top salt, there are issues, rabbit-ears. There's a paper, famous paper by Fachi Liu, Scott Morton, Jacques Levet, yes, removing the rabbit ears. This is Chung Fu taking that last formula, imaging above a reflector, then taking that experiment below the reflector, yes? Now you're dealing with two-way waves above, yes? And he uses that G0dn. So you get a bright and dark for positive, negative reflection coefficient above and below. No rabbit ears. None of those artifacts. It's just an experiment. Just arrange it, yes? Okay, migrating multiples. Let's quickly talk about this. Thanks to, where's Professor Fang Lu? There's a famous paper Professor Fang Lu published in JSE that extends, if you like, this work of Chung Fu to layers, yes? In other words, predict the source and receiver, okay? And through layers. In practice, we're not advocating doing migration through discontinuity, yes? That's what you would do. That's a risky business. You have to be confident, yes, on that you have. We're talking about developing and delivering to you and describing exactly how to do migration that is equally effective at all frequency through smooth velocity, yes? That's what we're aiming at here. But for the purpose of seeing what happens to primaries and multiples, discontinuous is needed. If you have multiples in your data and you're trying to see what happens to multiples in migration, you better put discontinuities in your model or you're not producing the experiment. If you don't have discontinuities, you don't have multiples. You understand? You must have a medium with discontinuities to have internal for sure, even free surface. So this is showing you what happens. This is a movie, a video of what happens. In other words, you have data on the surface. And let's just go back. This story is linear. It says you do some sum on your data. You do some sum on your data. And first of all, this method does need the field in the derivative, but it's a one-way wave. You deghost it. In other words, what I said before, and you say, well, you change your mind different times in the morning. I said, if you give me P all around or the normal derivative all around, that's all you need. But here, we're saying, I'm not giving you anything on the bottom. So you have to give me P and the normal derivative on one side, yes? But we're deghosting before we do migration. The wave is up, yes? Up wave, homogeneous medium. We can get the normal derivative, yes? Just IKZ times. The normal derivative is an issue if you have two-way wave there. Yes, and then you have to measure it. Yes. Okay. So not to be concerned with this, but so the point is, this takes surface data, and there's a sum over receivers that brings the receiver down. Then a sum over sources that brings the source down. Okay, but basically, your data on the surface is linearly becoming data at depth. Linearly, yes. You can trace, therefore, the history of what is going on in the experiment at depth in terms of what were events that you originally measured. Yes. That's what we're going to do here, because we want to see how primaries and multiples in the original data, yes, affected the experiment at depth. Yes, we're tracing that. So that's just looking at a primary. The primary that's measured affects the primary here, and so on. Then it becomes the primary below. That's simple, yes? The data's, okay. Now, here's an example already that makes the point. And this is a free surface multiple. Whoop, how do we stop this? This will go on forever. Okay, anyway, what's going on here? Let's just draw it. You have a free surface, yes? You have a source and receiver. You have a reflector. You have a primary, and you have a free surface multiple, yes? That's what's measured, okay? Now, as you bring it down, let's say you're here. When you are here, this primary here, this primary becomes this primary, yes? And this free surface multiple becomes this free surface multiple. Whoop. You understand? The source and receiver are here now. So, because it's linear, one event moves to another event. It's just a linear, it's summing, yes? They're not multiplying events. It's not nonlinear, yes? So each event has its own trajectory into the subsurface, yes? So the point is, when you have a source and receiver over here, the original primary became this primary, and the original free surface multiple became this free surface multiple, yes? And you ask for t equals 0, only this primary counts. The free surface multiple here will be at non-zero time. So only the primary in the original data will contribute. Understood? The same exact thing for internal multiples. So if you had, and the math of that is in Professor Fang Lu's JSC paper. We're just showing you a cartoon. In other words, you can see it in the math that when you do the imaging, the multiple is behind, doesn't come in. The original primary comes into the primary at depth, to the image at depth. So that says that if you are convinced that you want to deal with Claerbout 3 imaging as extended by Stolt for the reasons we mentioned, and you give me a discontinuous medium, then multiples will cause no problem. You do not need to remove multiples if you can give me an accurate discontinuous medium, because I'll just take the source and receiver down, ask for t equals 0, yes? And the multiples are going to come in later, always, yes? So this whole project that we have multiple removal would cease to exist if we could do discontinuous migration. We don't do discontinuous migration, we do smooth velocity. For smooth velocity, it is an issue. If you have a smooth, so this goes on with other examples. Here's internal, showing the same. For smooth velocities, which is not what we just said, we made it, if you have a smooth velocity and you're taking primaries and multiples down, you have not made the experiment. Yes? Your source and receiver there is not what the source and receiver would be there. Yes? Because if you have primaries and multiples, you better have discontinuity, because multiples require discontinuity in the medium, yes? You understand? So if you assume a smooth velocity, you are not predicting a Claerbout 3 image, and the price of that is every multiple is going to give you an artifact, a false image, yes? And so it is one simple reason that multiples need to be removed today, because we, in practical migration, with very rare exceptions, top salt, deal with smooth, yes? And for smooth, if I take primaries and multiples through smooth, the primaries will give me the correct. I can arrange for a smooth to give the right location, but every multiple will give me a false image. And that's the reason multiples need to be removed, okay? So what about if recorded primaries are insufficient or inadequate? There are methods, and PGS is a lead company in this, of using, in other words, what the previous said is, if you have a complete set of primaries, get rid of the multiples, and that's all you need, yes? You got to get rid of the multiples if you have a smooth velocity. If you have an accurate discontinuous, don't get rid of them. Just image. It will make no difference whether you have multiples in or not, yes? The image only cares about primaries in your original data, if you could do discontinuous. Okay, so what is this about? The previous talk assumes that you have an adequate primary set, yes? If you don't, then there are methods developed that can use a recorded multiple and a primary sub-event of the multiple whereas, let's say this is a multiple. This is a weak multiple. What happened to the pen? All the pens are ending up here. You have to have, the multiple can't be that weak. You have a multiple here, yes? And imagine that you can have this recorded, where this has been source deghosted, but this receiver, you have kept the receiver ghost. In other words, you have, instead of having this, you want this ghost, yes, on the receiver side. Then the idea is, assume that you did not have, you had this measured, you had this known, yes, and you have not measured, you have not recorded this primary, this sub-event. Then if in a sense of RTM, you take this point and you let that be like a source, you take that as a source field going forward, and you take this back, you can get an approximate C2 image of this unrecorded primary, yes, an approximate RTM image of that primary. And there are discussions, and there are issues. First, of course, every method has issues. How are you going to predict a multiple without the sub-events? Yes? You have to have this and this measured to predict that that's a multiple. So people don't predict the multiple. They take the whole data and put it in. Yes? They put the whole data in. The multiples in the data could behave. The non-multiples are going to cause mischief. Okay? And in addition, let's say you thought that this was unrecorded, and in fact it was recorded. Yes? So nothing is, so what's the point? It depends, what do we advocate? It depends on your level of ambition, yes? If you are looking for amplitude analysis, yes, significant amplitude analysis at depth, then what we advocate is collect the data and do Stolt extended C3 for heterogeneous media, yes? If you have a data set and it's less than what you would want to be adequate, and of course in the real world that's always the case, that it is useful to get some improved image through that kind of, for a less ambitious type of objective, yes? Some structure, and you better hesitate if you're looking at amplitude. So it depends on your level of ambition. If you're extremely ambitious, collect more, yes? And no matter how much you collect, that could still be useful. This. You understand? It's trying to get some benefit from an unrecorded primary, less than having nothing. Oh, speaking of that business, okay, so this is all I'm going to say. But another thought. We had this business yesterday, changing the subject altogether. We need a data matrix, DPP, DPS, yes? All the pioneering work of Haiyan Zhang and Hong Liang, all of that work, it has this very stringent requirement. And what if you didn't collect it? So what's the use of it if you don't collect it? So Haiyan dealt with that issue because she did some tests with Doug Forster and Bob Keyes at ConocoPhillips, time-lapse issues. They only had PP data. Her method says, I want PS and everything else, yes? Well, what she did is she synthesized the PS, SS. She took the PP data, forgive me for saying this, and she took linear estimates of things from PP data, changes in lambda, mu, rho, and she took the mu change and rho, and she made approximate PS and SS data. The idea was that is not PS and SS data. Of course, we did it synthetically, it doesn't match, but it's better than putting zeros in. You understand? So what's the benefit of that direct method? You know in principle what you need, yes? And when things don't work, you can attribute to issues, yes? That's the point. It's not that we go and do that or don't do anything, yes? It gives you a framework. And so I hope I've given some sense of that Claerbout 3 and Claerbout 2 are different in terms of their treatment of frequency, that there is a method here for dealing with heterogeneous, and now we're going to have 3 talks that talk about quantifying that difference, yes? Quantifying the difference between RTM and how to actually implement, that Stolt extended Claerbout 3 for heterogeneous. You have a velocity, what should you do, yes? Exactly what should you do to assure that you've migrated through it without compromising frequency, yes? That's essential. So we'll return to that after those 3 talks to assure that that message is clear. Why don't we take a short break now, and then we'll have a set of talks that quantify those differences in terms of resolution.